Hi guys, continuing in the topic of calculus limits that we were working on. Today I'll be working on with you guys limits at infinity. That is, we should be looking at the behavior of the function at the end. What happens when we move on and on as far as the input is considered? So it basically involves two things. If the value of x increases without any bound, it goes on and on and on, which essentially means that x is tending towards plus infinity. It's increasing without any bound, right? If the value of x decreases without any bound, we write it as that x is tending towards, it's going small and small and small, it's going towards minus infinity. So the two things that we are here considered about, the two things that we are considered about here when we are talking about limits at infinity, it could be when x is tending towards plus infinity or x is tending towards minus infinity. For example, say we have to figure out x tending towards minus infinity 1 upon x. If x is tending towards minus infinity, 1 upon x will whatsoever be tending towards 0. So the limit will be 0. Say we want to find out what is the limit as x tends to plus infinity of 1 upon x. That's going to be 0 again. No matter whether x goes to minus infinity or plus infinity, 1 upon x will be giving you the limits. Let's try to understand why. Why is 1 upon x tending towards 0 in under both the situations? So see, essentially, if you see it graphically, if you will try to put values, give values to x, your 1 upon x graph could be when x is positive, 1 upon x will be positive. So therefore, the first quadrant where both x and y are positive, that will be the result. If x is negative, when x is negative, minus 1 upon x is also negative basically. So since 1 upon x is negative here, what's going to happen is you will be x and y both are negative. That is why the third quadrant. So your graphs clearly will be either in the first quadrant or it will be in the third quadrant, right? Now, what's happening here? So you give the value of x. X is 1, then y is 1. Here. X is minus 1, y is minus 1. See here. Then x is 2. Y is 1 upon 2. X is minus 2. You get minus 1 upon 2. So if I put it on a table out here, let's look at certain values of x and y, that is 1 upon x, and try to increase, keep increasing your x. So suppose x is minus, try to decrease, x. We are talking about minus infinity right now. So you have minus 1. At minus 1, 1 upon x is also minus 1. At minus 10, 1 upon x will be minus 0.1. It will be a decimal. Okay. At minus 100, it's going to be minus 0.0. At minus 1000, it's going to be minus 0.001. So basically, it's increasing. The value of y is actually increasing. Okay. It's increasing here. X is tending smaller and smaller, turning smaller and smaller. 1 upon x is actually increasing. It's actually increasing towards 0. Towards 0, if you may see that, right? And that's what is happening geometrically as well. When x is going, to minus infinity out here, y is increasing to 0. It's almost 0. On the other hand, let's also look at the graph and table for x and 1 upon x as x is increasing to plus infinity. So when x is 1, 1 upon x is 1. When x is 10, 1 upon x is 0.1. When x is 100, 1 upon x is 0.01, and so on and so forth. So that means when x is tending towards plus infinity, x is increasing. 1 upon x is actually decreasing. And this time, 1 upon x is decreasing towards 0. So if you will see the graph of it, what's happening essentially here is that, again, your graph is first quadrant and third quadrant. As x is going to plus infinity, that's here, your y is actually decreasing to almost 0. But it's never equal to 0, so that's why it will go parallelly. It will go parallelly here, okay? To the x-axis, it would be parallel to the x-axis, okay? So that's how you can create the entire graph of 1 upon x. Let's generalize this concept. Let's generalize this concept. So if the values of fx eventually get as close as we like to, say, a number L, as x increases without any bound, then we write it as limit x goes to plus infinity fx is equal to L. And similarly, if the values of fx get as close as we like to a number L, that is the limit is L, as x decreases without any bound. So x is decreasing without any bound, that means x is tending towards minus infinity, and the limit of fx is L. That's how we can generalize and write. Let us interpret it geometrically. Now, if this graph is provided to you, what's happening here? This is a horizontal line that you can see. This is a horizontal line which is depicting y is equal to some value L. And what's happening here is that this graph, it is sort of going parallel to this y equals to L after a point. Now, what is that after a point? This is like x is increasing. It's going on and on and on. It is going towards infinity. This graph basically depicts when x is going to plus infinity, fx is giving you L. Can you see what's happening here? Here you have a line to which the graph is like almost parallel. Okay, parallel to the x-axis, horizontal line, and to which the graph is parallel. That means this is a situation where you do get asymptote. This is where we get horizontal asymptote. Y equals to L is a horizontal asymptote. In the previous lecture, we worked with the infinite limits. That is, when you get limit as infinity plus or minus, you get vertical asymptote, right? Now here you're getting horizontal asymptote because the graph will be moving parallel to some line y equals to L horizontally. Similarly, if you notice this one, so this is your x-axis and this is, say, 0. So you again have y equal to L is some function here. And this is, you can see this is a horizontal line out here. This is a horizontal line here, and your graph is moving parallel. After a certain point, it's moving parallel to this horizontal line. Again, it's a scenario where you have horizontal asymptote. But this time what's happening? The x that you are seeing is moving towards minus infinity, okay? So here the limit as x goes to minus infinity fx is equal to L. And this, if either of the things hold, you have a horizontal asymptote at y equal to L. If either of the limits hold, we call this line y equal to L a horizontal asymptote. Few laws which will come very handy when we are solving problems associated to limits at infinity. Number one, limit as x goes to plus infinity, fx to the power n. If you want to figure out the limit of fx to the power n, it's same as taking the limit of fx as x goes to infinity and take the power then. Similarly, when x goes to minus infinity, fx to the power n, you can take first the limit and then take the power n, okay? For example, also, first of all, yeah, some more limits here. And then I'll go to the examples. Limit x tends to plus infinity, k times fx. K times fx, you scale up or down your function. You can scale up, down the limit. It's going to be the same thing. Similarly, for minus infinity, if you scale up, down the function, it's same as scaling up or down, scaling down the limit, it's going to be the same thing. If you have a constant function, so whether x is tending towards minus infinity or plus infinity, that will not make any difference. The function will remain constant. Now, examples. So, for example, if we want to figure out what is the limit as x goes to plus infinity of 1 upon x to the power n, what we can actually do is we can take the limit inside and we can say this will be same as limit 1 upon x as x goes to infinity to the power n. So, this will actually be just 0. Similarly, if x is going to minus infinity, it is same as saying limit x tends to minus infinity 1 upon x whole to the power n, and that also will give you 0, right? So that's what the first law said. It's just an example to show it. Okay, interestingly, sometimes fx also might increase or decrease without any bound as x or minus as x is going to plus infinity or x is going to minus infinity. That is, at infinity, you are getting an infinite limit. That is possible. So getting at infinity infinite limits. So that's a scenario, for example, where say limit x tends to plus infinity of x. So clearly, since x is tending towards plus infinity, the limit is plus infinity. Similarly, if x is limit x tends to minus infinity of x, we have to find out. It's going to be minus infinity. Similarly, if I have to find out what is the limit as x tends to infinity of x squared, it is going to be plus infinity. Limit x tends to minus infinity of x squared, it will again be plus infinity. It will again be plus infinity, right? Now, what is the limit as x tends to plus infinity of x to the power n? So we had square plus infinity n. Since x is tending towards plus infinity, it is going to be plus infinity. But what if x is tending towards minus infinity? Then it would depend how many times is x getting multiplied by itself. Is it odd number of times or even number of times? So n odd, something else will happen. N even, something else will happen. When n is odd, that means I will get minus infinity as the limit. When n is even, like x squared, x to the power 4, you will get, even as x is tending towards minus infinity, you will get plus infinity, right? Let's understand some polynomial functions, some important kind of functions. Polynomial functions are pretty important in mathematics. Let's understand their end behavior. When I say end behavior, that means, what happens as x is tending towards infinity or minus infinity. Now, suppose you have a polynomial a0 plus a1x plus a2x squared plus so on and so forth till a(n) x to the power n. As x is tending towards minus infinity, what's going to happen to this? What you would notice here is that assuming that an is not equal to 0, the limit of this polynomial would actually match the limit or the behavior of this polynomial as x is tending towards minus infinity will be same as, it will match the behavior of the highest degree term, that is an x to the power n. So whether it is x tending towards plus infinity or minus infinity, even with plus infinity, same polynomial, the behavior will be same as the limit as x tends to plus infinity of an x to the power n. And I'm sure you understand why, because you were talking about in terms of infinities. What is an and what is it attached to x to the power n, the highest? So, when you have the highest, it would really depend. It would either make it bigger, depending on what is n. Either even minus infinity would turn into plus infinity, or if it's odd, minus infinity would become minus infinity. Also, mathematically speaking, what exactly we are trying to, analyze here how this matches the highest degree term, behavior of the highest degree term, is because if you take x to the power n common, just take x to the power n common. If you take x to the power n common, your polynomial would turn into a naught upon x to the power n plus a1 upon x to the power n minus 1 plus a2 upon x to the power n minus 2 plus so on and so forth plus an. Right? Now, if you see x is tending towards either plus infinity or minus infinity. Any case, take one case, whichever might be the case. This expression will turn into 0. This expression will turn into 0. This expression will turn into 0. Only this expression will remain. So that means you are actually at the end, you would be left with an x to the power n. So whatever is the limit of as x goes to infinity, plus infinity or minus infinity, an x to the power n is what is your answer for the polynomial given to you. Suppose we have to find out the limit as x tends to minus infinity, 7x to the power 5 minus 4 times x cubed plus 2x minus 9. What will be the result? Can you see that clearly it would be dependent on 7x to the power 5? So it's same as limit x tends to minus infinity, 7x to the power 5. And with minus infinities, just be a little careful. See, because here you have x to the power 5. It's an odd power. So you will end up with minus infinity. Had it been even power, then you would have got plus infinity, right? So just be careful with that. Okay, also another kind of functions which are very important in order to analyze as x is tending towards plus minus infinity. They're the rational functions. So rational functions, when you divide two polynomial functions, you get like a rational function, okay? So for example, if we have to find out the limit as x tends to plus infinity of 3x plus 5 upon 6x minus 8, what would you try to do? The trick to find out limit in these scenarios for rational functions at infinity is to divide the entire expression by the highest power in the denominator. So divide the numerator as well as the denominator by the highest power in the denominator. And the highest power in the denominator is x to the power 1. Highest power in the denominator is x to the power 1. So let's divide. Divide numerator, you will get 3 plus 5 upon x. Denominator, you will get 6 minus 8 upon x. Now, what essentially happens when we do this? The idea, I had thrown that idea before when we took some everything common. The idea here is that you create zeros, like we created zeros in the polynomial thing. So what happens is that you are creating zeros. When you will put infinity in 5 upon x and 8 upon x, clearly that will become 0. Constant will remain constant. So this is constant 3 plus 0, constant 6 minus 0 once you put the limit as x tends to infinity. So hence what you will get is 3 by 6, which can be further reduced to 1 by 2. So that's what you do. And how we are able to take the limit like this? See, limit has a property that limit can go inside. So what you're doing is you're taking the limit of the numerator and you're taking the limit of the denominator. Okay. In the numerator, 3 is just a constant. So it's 3 plus limit of 5 by x upon 6 minus limit of 8 by x. And the limit of 5 by x and 8 by x is as x is tending towards infinity. Okay, I've not written that here. There's no space. X is still tending towards infinity. So that's how you find these kind of limits. Let's take another case here. X is tending towards minus infinity, 4x square minus x upon 2x cube minus 5. Now, what I will do, divide by the highest power in the denominator. Divide by the highest power in the denominator. Don't forget that, in the denominator. Why in the denominator? So that we are able to create zeros. Otherwise, how will we create zeros? So more zeros will get created when you divide by the highest power in the denominator, because then infinity will be in the denominator. So you highest power in the denominator is x cube. So divide. So 4x square upon x cube minus x upon x cube upon 2 minus 5 upon x cube. In other words, we are looking at the function 4 upon x minus 1 upon x square upon 2 minus 5 upon x cube. Now you're looking at limit as x tends to minus infinity. Limit as x tends to minus infinity. Your numerator is turning 0. Since your numerator is turning 0, that means the limit has to be 0 only. Okay. So this time the limit is actually just 0. It's 0 minus 0 upon 2 minus 0. In other words, it's just 0. So the end behavior of a rational function matches the end behavior of the quotient of the highest degree term in the numerator divided by the highest degree term in the denominator. That's what you must have seen is happening. Since the numerator becomes 0 only here, that's why you're getting 0. Since here it is 3 and 6 here, so you got 3 upon 6. So yes, the end behavior of a rational function matches the end behavior of the quotient of the highest degree term in the numerator divided by the highest degree term in the denominator. So always remember, the basic trick is divide by the highest degree in the denominator. The whole idea is to create zeros, as many zeros as possible. That's what you try to do when you are trying to figure out limits, so that your calculations are simpler. Remember, in maths, we're trying to simplify our lives rather than complicating it. Okay, so let's twist it a bit and involve radicals also. So let's involve radicals. So whatever this question is, the moment you see that you have to find a limit at infinity, you have to think of the trick, divide by the highest power in the denominator. What's the highest power in the denominator? Here, x to the power 1. Now, if you see, you take x, you divide by x, what's going to happen is that you're basically dividing by the absolute value of x. I can take that inside. Why I'm taking absolute value of x is because I will have to take it inside the square root. So I'm going to say absolute value of x here, whole thing upon 3x minus 6 upon absolute value of x. Absolute value I'm writing only because I have to take it inside the square root. So this would make it x square plus 2 upon square root of x square. Square root of x square is x mod x. That is why I've taken that. 3x minus 6. Now I can write x here because I know that x is greater than 0. It's going towards plus infinity, right? So I'm just going to write x here now. But here, what's going to happen is that you will have inside the square root. Now you can combine the square roots and you get x square upon x square plus 2 upon x square, whole thing upon 3 minus 6 upon x. That is square root of 1 plus 2 upon x square, whole thing upon 3 minus 6 upon x, which will give you 1 from the numerator and 3 from the denominator. Hence, the answer is 1 upon 3. Now, I think the next one is same, except for you have x tending towards minus infinity. Since you have x tending towards minus infinity, that's why I was very, I did introduce modulus of x here because you have square root. So just be careful there. Now you have square root of x squared plus 2 whole thing divided by modulus of x upon 3x minus 6 whole thing divided by modulus of x. Now this time I will be taking it inside and it will be x squared by x squared plus 2 upon x squared whole thing upon. See, this time x is tending towards minus infinity. So therefore this will be minus x. Therefore this will be minus x. That's the difference between the previous question and this one. And this is happening because your absolute value of x is x when x is greater than or equal to 0 and it's minus x when x is less than 0. So clearly minus infinity falls in the second category. Okay. Now this will give you square root of 1 plus 2 upon x square upon minus 3 plus 6 upon x. So as x is tending towards minus infinity, you get 1 upon minus 3. That is, the limit is actually minus 1 by 3 and not 1 by 3. So there you have to be a little, cautious when you're dealing with minus infinity. That's the reason why I took up the same expression, but with two limits extending towards plus infinity and minus infinity with radical square root.